go
There?
yeah.
Is that not tilted anymore?
Yeah, it's horizontal.
That's good?
Yeah, but you're too zoomed up. Okay, let me sit over here.
Oh, that's where I'm gonna sit.
No,
Oh.
I'm your feet.
Oh, you're my.
I'm your helper.
Oh, okay. I think I need to go a little higher.
Why?
It just looks like it's like hanging down.
Well, you're blocking the Korean flag, right?
It's fine. I need more flags, so it's okay.
No, it's not okay. Do it like this,
What? That?
like this. Don't block it.
But anyways, I wanted to actually lift it up. I think I need to lift it up from here. Yeah, see, that looks a little bit more. Just a little bit more. Hold on. Oh, there you go. Good.
That high?
Yeah, I wanted to see the flag for you.
You should. The main focus, babe, should be you, not the flag.
Yeah, but I finally like put some stuff in the room. I'm happy.
Yeah.
Yeah. Okay. I think it's good. Good, good. Thank you.
Mm-hmm.
I'm gonna work out later today. And boom.
Boom shakalaka.
Boom, shakalaka. Yeah, I actually need to cut it a little bit more. I think I had any scissors, huh?
Oh,
Huh? Steady.
he's dead.
Can you stop? It's okay.
8 a.m. Print a copy of your ACT admission ticket.
Can't have these here because then it's gonna go mold. There's a lot of water. oatmeal. You want some?
Huh?
Making some oatmeal bread. You don't want it? Okay. Well, I'll be back. It's just what I usually get anyways. Oh, I forgot to take the cup down. I forgot to take the cup down, huh? I think we start here.
Oh, you're doing physics?
Yeah, we'll do it for this. Yeah, vectors and scalars.
Yeah. I don't want to do it. You wanna look me up?
Okay. Where's my other pill? Have you seen my B12?
Huh?
Have you seen my B12?
No. Wait, let me get my shirt and we can go on.
Sure. Mm-hmm. Seriously. I need to withdraw. You know what's in the B12?
Okay. Has it fall?
No, but actually, can you help me move the other one up again?
Which one?
The charger thing?
Yeah.
Yeah.
Oh, it fell again?
Yeah.
Sure. I don't know, babe.
Okay.
Look. Found it? Where'd you put it?
In the bathroom?
Maybe.
Maybe in the bathroom. Okay.
Can't find it.
I just suddenly end up in the table.
Huh?
I just end up in the table.
Maybe there's a ghost here.
You saw it was missing, right? Or no?
I'm scared.
But did you see it was empty? It was empty?
Can you actually check the footage?
No, but you saw, right? I looked. There wasn't here. Or am I going crazy?
Oh my god.
You were here, right?
I didn't see it.
You didn't see it before.
Someone's playing with you.
Is someone in the room? Is someone in the room with me? Is it you? No? You gotta make that strange, right? You got the keys or no?
Yeah.
Oh.
happening in one dimension. You can go forward or back. So you can go forward or back, or right or left, or you can go up or down. What I want to start to talk about in this video is what happens when we extend that to 2 dimensions, or we can even just extend what we're doing in this video to 3 or 4, really an arbitrary number of dimensions. What I want to do in this video is talk about the difference between vectors, and scalars. And they might sound like very complicated ideas, but we'll see over the course of the videos that they're actually very simple ideas. So first I'll give you a little bit of a definition, and then I'll give you a bunch of examples. And I think the examples will make things super clear. Hopefully they'll make things super clear. A vector is something that has a magnitude, and or you can kind of view that as a size, and it has a direction. So and it has a direction. And it has a direction. A scalar only has a magnitude or size. And if that doesn't make sense to you, it will hopefully make sense to you in a second when I show you an example. For example, let's say that I have let's say that that's the ground right there. Let me do the ground in a more appropriate light color. So this is here. And let's say that I pick and I have a brick here. I have a brick on the ground. And I pick up that brick and I move it over to this place right over here. So I move the brick right over there. And then I take a ruler out and I say, wow, I've moved the brick. I have moved the brick 5 meters. I have moved the brick 5 meters. So my question to you is, my measurement of 5 meters, is it a vector or a scalar? Well, if I just tell you 5 meters, you just know the size of the movement. You just know the magnitude of the movement. So if someone were to just say 5 meters, this is a scalar quantity. And when we're referring to moving something or how much something has, I guess, changed its position, and I don't give you the direction, we're talking about distance. And I'm assuming you've heard the word distance. How far of a distance has something traveled? So this is distance. So we could say that this block or this brick, because of my picking it up and moving it, has moved a distance of 5 meters. But if I didn't show you this picture here and someone just told you that it moved a distance of 5 meters, you wouldn't know if it moved to the right 5 meters, you wouldn't know if it moved to the left 5 meters, if it moved up or down or in or out, or you don't know what direction it moved 5 meters. You just know it moved 5 meters. If you want to specify that, so we could say that this brick right over here, that it moved 5 meters to the 5 meters to the left. 5 meters to the left. Now we have specified a magnitude right over there. So that is a magnitude. And we have specified a direction to the left. So you now explicitly know that they went 5 meters to the, oh, sorry, it should be 5 meters to the right. Let me change that. So 5 meters to the, that's why the direction to the right is what it got moved. It started here, it went 5 meters to the right. So once again, the magnitude is 5 meters, and the direction is to the right. So what I've just described to you right here is a vector quantity. So this, all of this business right over here, this is a vector. And when you talk about the movement, the change in position, and you give its direction, the vector version of distance, I guess you could call it, is displacement. So this right here is displacement. So the correct thing to say, you would say that this brick has been displaced 5 meters to the right, or it has been moved a distance of 5 meters. Distance is a scalar quantity. I didn't tell you what direction we moved it in. Displacement is a vector quantity. We told you that it is to the right. Now let's explore this if we talk about the actual, well, we'll talk about the speed or velocity of something. So let's say that this 5 meters was traveled, and let's say that the change in time, and when let me just, because you're probably not familiar with what that means. So let's say that the change in time right here, when I moved this block 5 meters, let's say that it was, I don't know, let's say that the change in time was 2 seconds. So maybe right when the block started moving, maybe on my stopwatch it said 0, and then on my stopwatch when it stopped moving, it said, or when it got to this position, I should say, when it left from this position, my stopwatch said 0. When it got to this position, my stopwatch said 2 seconds. So the change in time, or the duration we're dealing with, is 2 seconds. And this is, for all we know, time only goes in the positive direction. So you could assume that it's, well, you could pick that as a vector or a scalar quantity, I guess, because there's only one direction for time, as far as we know, or at least in what we're going to deal with for the simple physics. So what's a measure of how fast this thing moved? So how fast did this thing move? So we could say it moved 5 meters in 2 seconds. Let me write this down. So it moved 5 meters. It moved 5 meters per 2 seconds. Per 2 seconds. Or we could write this as 5 halves of a meter per second. Or 5 divided by 2 is what? 5 divided by 2 is 2.5 meters per second. Meters per second. Meters per second. This right here is just the 5 divided by 2. Let me make that clear. That right there is just the 5 divided by the 2. So my question to you, this 2.5 meters per second tells you how far it traveled in a certain amount of time. Is this a vector or a scalar quantity? It is telling you how fast it went, but is it giving you just a size of this of how fast it went, or is it also giving you direction? Well, I don't see any direction here. So this is a scalar quantity. And the scalar quantity for how fast something is going, is speed. So we could say that the speed of the brick is 2.5 meters per second. Now, if we do the same calculation, we say it went if we say it went 5 meters, I'll just write m for meters, 5 meters to the right in 2 seconds, then what do we get? We get 2.5, once again, 2.5 meters per second. I'll just abbreviate them as meters per second to the right. So is this a vector or a scalar quantity? I'm telling you the magnitude of the speed. That's right here. This is the magnitude, 2.5 meters per second. And I'm also telling you the direction, to the right. So this is a vector quantity. And when you specify both the speed and the direction, so the 2.5 meters per second is a scalar, and the direction, you are talking about velocity. So easy way to think about it. If you're thinking about change in position and you specify the direction of the change in position, you're talking about displacement. If you're not talking about the direction, you want the scalar version, you're talking about distance. If you're talking about how fast something is going and you give the direction that it's going in, you're talking about velocity. If you don't give the direction, you are talking about speed. Hopefully that helps you a little bit. In the next video, we're going to start working with these a little bit to start solving some basic questions about how fast something is going, or how far it might travel, or how long it might take it to get someplace. With classical, all the problems we've been dealing with so far have essentially been happening in one dimension. You could go forward or back. So you could go forward or back, or right or left, or you could go up or down. What I want to start to talk about in this video is what happens when we extend that to 2 dimensions, or we can even just extend what we're doing in this video to 3 or 4, really an arbitrary number of dimensions. Although if you're dealing with classical mechanics, you normally don't have to go more than 3 dimensions. And if you're going to deal with more than 1 dimension, especially in 2 dimensions, we're also going to be dealing with 2-dimensional vectors. And I just want to make sure through this video that we understand at least the basics of 2-dimensional vectors. Remember, vector is something that has both magnitude and direction. So the first thing I want to do is just give you a visual understanding of how vectors in 2 dimensions would add. So let's say I have a vector right here. That is vector A. So once again, its magnitude is specified by the length of this arrow, and its direction is specified by the direction of the arrow. So it's going in that direction. Let's say I have another vector. Let's call it vector B. Let's call it vector B. It looks like this. And what I want to do in this video is think about what happens when I add vector A to vector B. So there's a couple of things to think about when you visually depict vectors. The important thing is, for example, for vector A, that you get the length right and you get the direction right. Where you actually draw it doesn't matter. So this could be vector A. This could also be vector A. Notice it has the same length and it has the same direction. This is also vector A. I could draw vector A up here. It does not matter. I could draw vector A up there. I could draw vector B. I could draw vector B over here. It's still vector B. It still has the same magnitude and the direction. Notice, we're not saying that its tail has to start at the same place that vector A's tail starts at. I could draw vector B over here. So I can always have the same vector, but I can shift it around. So I can move it up there as long as it has the same magnitude, the same length, and the same direction. And the whole reason I'm doing that is because the way to visually add vectors, if I wanted to add vector A, plus vector B, and I'll show you how to do it more analytically in a future video, I can literally draw vector A. I draw vector A, so that's vector A right over there. And then I can draw vector B, but I put the tail of vector B to the head of vector A. So I shift vector B over so its tail is right at the head of vector A, and then vector B would look something like this. It would look something like this. And then if you go from the tail of A all the way to the head of B, and you call that vector C, that is the sum of A and B. That is the sum of A and B. And it should make sense if you think about it. If these were, let's say these were displacement vectors. So A shows that you're being displaced this much in this direction. B shows that you're being displaced this much in this direction. So the length of B in that direction. And I were to say you have a displacement of A, and then you have a displacement of B. What is your total displacement? So you would have had to be, I guess, shifted this far in this direction, and then you would be shifted this far in this direction. So the net amount that you've been shifted is this far in that direction. So that's why this would be the sum of those. Now we can use that same idea to break down any vector in 2 dimensions into its, we could say, into its components. And I'll give you a better sense of what that means in a second. So if I have vector A, let me pick a new letter. Let's call this vector X. Let's call this vector X. I can say that vector X is going to be the sum of this vector right here in green and this vector right here in red. Notice X starts at the tail of the green vector and goes all the way to the head of the magenta vector. And the magenta vector starts at the head of the green vector and then finishes, I guess, well, where it finishes is where vector X finishes. And the reason why I do this, and this hopefully from this explanation right here says, okay, look, the green vector plus the magenta vector gives us this X vector. That should make sense. I put the head of the green vector to the tail of this magenta vector right over here. But the whole reason why I did this is if I can express X as the sum of these 2 vectors, it then breaks down X into its vertical component and its horizontal component. So I could call this the horizontal component, or I should say the vertical component, X vertical, and then I could call this over here the x horizontal. Or another way I could draw it, I could shift this x vertical over. Remember, it doesn't matter where I draw it as long as it's the same magnitude and direction. And I can draw it like this, x vertical. And so what you see is that you can express this vector x. You can express this vector x. Let me do the same colors. You can express this vector x as the sum of its horizontal and its vertical components. As the sum of its horizontal and its vertical components. And we're going to see over and over again that this is super powerful, because what it can do is it can turn a two-dimensional problem into two separate one-dimensional problems, one acting in a horizontal direction, one acting in a vertical direction. Now let's do it a little bit more mathematical. I've just been telling you about length and all of that. Let's actually break down. Let me just show you what this means to break down the components of a vector. So let's say that I have a vector that looks like this. Let me do my best to. So let's say I have a vector that looks like this. Its length is 5. So let me call this vector A. And I will say, so vector A's length is equal to 5. And let's say that its direction, we're going to give its direction by the angle between the direction it's pointing at and the positive x-axis. So maybe I'll draw an axis over here. So let's say that this right over here is the positive y-axis going in the vertical direction. This right over here is the positive x-axis going in the horizontal direction. And to specify this vector's direction, I will give this angle right over here. And I'm going to give a very peculiar angle, but I picked this for a specific reason, just so things work out neatly at the end. And I'm going to give it in degrees. It's 36.8699 degrees. So I'm picking that particular number for a particular reason. And what I want to do is I want to figure out this vector's horizontal and vertical component. So I want to break it down into something that's going straight up or down and something that's going straight right or left. So how do I do this? Well, one, I could just draw them visually, see what they look like. So its vertical component would look like this. Its vertical component would look like this, and its horizontal component would look like this. Its horizontal component would look like this. The horizontal component, the way I drew it, would start where vector A starts and go as far in the x direction as vector A's tip, but only in the x direction. And then you need to get back to the head of vector A, you need to have it. Its vertical component. And we can sometimes call this, we could call the vertical component over here A sub y, so that it's moving in the y direction. And we could call this horizontal component A sub x. And what I want to do is I want to figure out the magnitude of A sub y and A sub x. So how do we do that? Well, the way we drew this, I've essentially set up a right triangle for us. This is a right triangle. We know the length of this triangle, the length of this side, or the length of the hypotenuse. That's going to be the magnitude of vector A. And so the magnitude of vector A is equal to 5. We already knew that up here. So how do we figure out these sides? Well, we could use a little bit of basic trigonometry. If we know the angle and we know the hypotenuse, how do we figure out the opposite side to the angle? So this right here is the opposite side to the angle. And if we forgot some of our basic trigonometry, we can relearn it right now. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we have the angle, we want the opposite, and we have the hypotenuse. So we could say hypotenuse. Tangent is opposite over adjacent over hypotenuse. We forgot some of our basic trigonometry. We can relearn it right now. SOHCAHTOA. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. So we have the angle, we want the opposite, and we have the hypotenuse. So we could say that the sine of our angle, the sine of 36.899 degrees is going to be equal to the opposite over the hypotenuse. The opposite side of the angle is the magnitude of our y component. Is going to be equal to the magnitude of our y component, over the magnitude of the hypotenuse, over this length over here, which we know is going to be equal to 5. Or if you multiply both sides by 5, you get 5 sine of 30.
Excuse me.
.899 degrees is equal to the magnitude the vertical component, the magnitude of the vertical component of our vector A. Now, before I take out the calculator and figure out what this is, let me do the same thing for the horizontal component. Over here, we know this side is adjacent to the angle, and we know the hypotenuse. And so cosine deals with adjacent and hypotenuse. So we know that the cosine of 36.899 degrees is equal to, cosine is adjacent over hypotenuse, is equal to the magnitude of our x component over the hypotenuse. The hypotenuse here has, or the magnitude of the hypotenuse, I should say, which has a length of 5. Once again, we multiply both sides by 5, and we get 5 times the cosine of 36.899 degrees. Is equal to the magnitude of our x component. So let's figure out what these are. Magnitude of our vertical component is equal to 3, and then let's do the same thing for our horizontal component. We get it to be 4. So what we see here is a situation where we have, this is a classic 3, 4, 5 Pythagorean triangle. The magnitude of our horizontal component is 4. The magnitude of our vertical component, the magnitude of our vertical component right over here is equal to 3. And once again, you might say, Sal, why are we going through all this trouble? And we'll see in the next videos, if we say something has a velocity in this direction of 5 meters per second, we can actually say that we can break that down into 2 component velocities. We can say that that's going in the upwards direction at 3 meters per second, and it's also going to the right in the horizontal direction at 4 meters per second. And it allows us to break up the 9x. So the classic 3, 4 horizontal component is 4. The magnitude of our vertical component, the magnitude of our vertical component right over here is equal to 3. And once again, you might say, Sal, why are we going through all this trouble? And we'll see in the next videos, if we say something has a velocity in this direction of 5 meters per second, we can actually say that we can break that down into two component velocities. We can say that that's going in the upwards direction at 3 meters per second, and it's also going to the right in the horizontal direction at 4 meters per second. And it allows us to break up the problem into two simpler problems, into two one-dimensional problems, instead of a bigger two-dimensional one.
Good afternoon. We've done a lot of work with vectors, and in a lot of the problems when we launch something into, in the projectile motion problems, or when we were doing the inclined plane problems, we always broke, I always gave you a vector. Like I would draw a vector like this. I would say, something has a velocity of 10 meters per second. It's at a 38-degree angle. And then I would break it up into the x and y components. So, if I called this vector v, I would use a notation v sub x, and the v sub x would have been this vector right here. V sub x would have been this vector down here, the x component of the vector. And then v sub y would have been the y component of the vector, and it would have been this vector. So this was v sub x, this is v sub y, right? And hopefully by now it's second nature of how we would figure these things out. V sub x would be 10 times cosine of this angle. Cosine of 30 degrees, which I think is square root of 3 over 2, but we're not worried about that right now. And v sub y would be 10 times the sine of that angle. This hopefully should be second nature to you. If it's not, you can just go through SOHCAHTOA and say, well, the sine of 30 degrees is the opposite of the hypotenuse, and we get back to this. But we've reviewed all of that. You should review the initial vector videos. But what I want you to do now, because this is useful for simple projectile motion problems, but once we start dealing with more complicated vectors, and maybe we're dealing with multi-dimensional vectors, three-dimensional vectors, or we start doing linear algebra where we do n-dimensional vectors, we need a coherent way of, an analytical way, instead of having to always draw a picture, of representing vectors. So what we do is we use something that I call, and I think everyone calls, unit vector notation. So what does that mean? So we define these unit vectors. Let me draw some axes. And it's important to keep in mind, this might seem a little confusing at first, but this is no different than what we've been doing in our physics problems so far. So let me draw the axes. Draw the axes right there. Let's say that this is 1, this is 0, this is x. Oh, sorry, what am I doing? This is 2. 0, 1, 2. I don't know. I must have been writing in Arabic or something going backwards. This is 0, 1, 2. That's not a 20. And then let's say this is 1. This is 2 in the y direction. I'm going to define what I call the unit vectors in 2 dimensions. So I'm going to first define a vector. I'll call this vector I. And this is the vector. It just goes straight in the x direction. It has no y component, and it has a magnitude of 1. So this is I. We denote the unit vector by putting this little cap on top of it. There's multiple notations. Sometimes in a book, you'll see this I without the cap and it's just boldface. There's some other notations, but if you see I and not in the imaginary number sense, you should realize that that's the unit vector. It has magnitude 1 and it's completely in the x direction. And I'm going to define another vector, and that one is called j. And that is the same thing, but in the y direction. That is the vector j. You put a little cap over. So why did I do this? Well, if I'm dealing with 2 dimensions, and as later we'll see in 3 dimensions, there'll actually be a third dimension, and we'll call that k, but don't worry about that right now. But if we're dealing in 2 dimensions, we can define any vector in terms of sum of these 2 vectors. So how does that work? Well, what this vector here, let's call it v, right? This vector v is the sum of its x component plus its y component, right? When you add vectors, you can put them head to tail like this, and that's the sum. So hopefully, knowing what we already know, we knew that the vector v is equal to its x component plus its y component. When you add vectors, you essentially just put them head to tails, and then the resulting sum is kind of where you end up, right? So it would be if you added this vector and then you put this tail to this head and you end up there, so you end up there. So that's the vector. So can we define v sub x as some multiple of I of this unit vector? Well, sure. V sub x completely goes in the x direction, right? But it doesn't have a magnitude of 1. It has a magnitude of 10 cosine of 30 degrees. So its magnitude is 10. So this is, let me draw the unit vector up here. This is the unit vector I. It's going to look something like this in this. So v sub x is in the exact same direction, and it's just a scaled version of this unit vector. And what's its what multiple is it of that unit vector? Well, the unit vector has a magnitude of 1. This has a magnitude of 10 cosine of 30 degrees. So I think that's what, like 5 square roots of 3 or something like that. So we can write v sub x as, we could write v sub x. I keep switching colors to keep things interesting. We can write v sub x is equal to 10 cosine of 30 degrees times, that's the degrees, times the unit vector I. Let me stay in that color so you don't get confused. Times the unit vector I. Does that make sense? Well, the unit vector I goes in the exact same direction, but the x component of this vector is just a lot longer. It's 10 cosine 30 degrees long. And I can, that's equal to cosine of 30 degrees is square root of 3 over 2. So that's 5 square roots of 3 I. Similarly, we can write the y component of this vector as some multiple of j. So we could say v sub y, the y component. Well, what is sine of 30 degrees? Sine of 30 degrees is 1/2. So 1/2 times 10. So this is 5. So the y component goes completely in the y direction. So it's just going to be a multiple of this vector j, of the unit vector j. And what multiple is it? Well, it has length 5, while the unit vector has just length 1. So it's just 5 times the unit vector j. So how can we write the vector v? Well, we know the vector v is the sum of its x component and its y component. And we also know, so this is the whole vector v. What's its x component? Well, its x component can be written as a multiple of the x unit vector. That's that right there. So you can write it as 5 square roots of 3 I plus its y component. So what's its y component? Well, its y component is just a multiple of the y unit vector, which is called j with a little funny hat on top. And that's just this. It's 5 times j. So what we've done now by defining these unit vectors, and I can switch this color just so you remember that this is I, that this unit vector is this, is using unit vectors in 2 dimensions, and we can eventually do them in multiple dimensions. We can analytically express any 2-dimensional vector instead of having to always draw it like we did before and having to break out its components and always do it visually. we can stay in kind of analytical mode and non-graphical mode. And what makes this very useful is that if I can write a vector in this format, I can add them and subtract them without having to resort to visual means. And what do I mean by that? So if I have, if I define some vector A is equal to, I don't know, 2I plus 3j, and I have some other vector, this is a vector, and I have some other vector B, this little arrow just means it's a vector. Sometimes you'll see it as a whole arrow. Some as, I don't know, 10I plus, I don't know, 2j. If I were to say what's the sum of these two vectors, A plus B, before we had this unit vector notation, we would have to draw them and put them heads to tails, and you had to do it visually, and it would take you a lot of time. But once you have it broken up into the x and y components, you can just separately add the x and y components. So vector A plus vector B, that's just 2 plus 10 times I plus 3 plus 2 times j. And that's equal to 12I plus 5j. And something you might want to do, or maybe I'll do it in a future video, is actually draw out these two vectors and add them visually, and you'll see that you get this exact answer. And as we go into further videos or future videos, you'll see how this is super useful once we start doing more complicated physics problems, or once we start doing physics with calculus. Anyway, I'm about to run out of time on the 10 minutes, so I'll see you in the next video.
Set up a timer for the next one.
Welcome back. In the last video, I just, at the end of the video, like I always do, to confuse you, I told you that if I had two vectors, and let me just make up some new ones just so I can draw them visually in a second or two. Let's call the first vector A. We'll do a different color. This toothpaste color is getting monotonous. Do something. So let's call the first vector A, and I don't know, let's say it's, let me make it interesting. Let me say it's minus 3 times the unit vector I plus 2 times the unit vector J. And then I have vector B. And that is equal to, I don't know, let's say it's 2I, 2 times the unit vector I, plus, I don't know, let me say 4 times the unit vector J. In the last video, I said, well, the whole reason why this unit vector notation is even, well, one of the reasons, we'll see that there are many reasons why it's useful, but one of the really cool things about it is, before when we added vectors, we would put them head to tails and then draw it visually, and then we'd have this new vector, and we really had no way of expressing it without drawing it. But when we write things as multiples of the unit vectors, we don't have to draw it. And it's actually very easy to add vectors. And how do we do it? We just add the x components and we add the y components. So we said that these two vectors, A plus B, these little weird arrows on top, that's just saying that those are vectors, that equals, oh, this should be an equal sign, equals, not equals, that's equals. Okay, so it's minus 3 plus 2I, arbitrary switch colors because it's getting monotonous, plus 2 plus 4J. We just added the x components, or the multiples of I, and we added the y components, or just the multiples of j, right? Because I was the unit vector in the x direction, and j was the unit vector in the y direction. And we get, what's minus 3 plus 2? That's minus 1. So we get minus 1i, or that could just be minus I, but I'll write it 1, just because we're just getting warmed up with unit vectors. So minus 1i plus 6j. And when I did that, you might say, well, Sal, I can't just take your word for it because you seem kind of a, not someone who should be believed blindly. So, and I think that's a valid opinion to have. So I will show you that this works by adding the vectors visually. So let's draw it, and I think this will give you a little better sense of unit vectors generally. Let me draw the axes. So that's my y-axis. X-axis. Make sure I have enough space to draw the unit vectors that we've drawn, or to draw the vectors that we've drawn. So that's just to show you that the axes go on forever. Just draw that arrow. All right. So let's see. This is 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. I think we should be able to now add them. I didn't have to waste all the space down here. So let's just first draw the vectors. Minus 3i plus 2j. So minus 3i. So minus 3i, just this right here is going to be a vector that looks something like this. So it's just minus 3 times the x vector, so it'll go to the left, right? Because I is 1 in the positive direction. So if we put a negative there, it flips it over. And we'll do a different color. So this is minus 3i, and then plus 2j. So plus 2j looks like this. Right, this is plus 2j. And if we were to add those two vectors visually, we can put them head to tails. And the way we could do that, we can either shift this vector up like this, and draw it up here, or we could shift this vector and put its tail to this vector's head. But either way, so let's shift this one up. So we shift it up like that. Remember, we're just doing the head to tails visual addition method of vectors. So I just put this tail to this head. And what do we get? So vector A will look like this. And I'm going to do it in the same color as vector A, just so I have a feeling that this diagram might get complicated. I wanted to use a line tool. Undo. Line tool. Okay, so this is vector A. That's what vector A looks like. And so we worked backwards. I gave you the x component and the y component, and then I added them together by doing the head to tails method. And so this is what vector A would look like. And instead of drawing it, a very easy representation is exactly what we did up here, the unit vector notation. And what's vector B look like? So it's 2i. I'm going to do a completely different color. It's 2i, so it's this vector. 2 times the unit vector I, that's this, plus 4j. 4j, 1, 2, 3, 4. So it looks like this. And let's take this one and shift it over to the left so we can put its tail to this vector's head. So like this. So vector B will look, I'll do it in red. I'll use a line tool. Vector B looks like this. Right, I just put its components head to tails, and that's how I got vector B. And if I were to add them visually, I would do it the same way that I added its components. I would put the tail of one vector to the head of the other and see get the resulting vector. So we could do it either way. Let's shift this A vector. Let's shift it in this direction and put it, because remember, vectors, we're just giving a magnitude and a direction. We're not necessarily giving a starting point. So you can shift them. You just can't change their orientation or their magnitude. And that's actually how you add them. You shift them and put them head to tails. That's when you add them visually. So let's put that A vector, let's put it up here. So if we have the A vector, it looks something like this. I know my A vector will look something like this, and I want it to work out, right? So the A vector, something like that. Remember, all I did is I took the same vector and I just shifted it so that it can start at the head, so its tail can start at the head of the B vector, right? So I just shifted the A vector. So this is still the A vector.
What do we do for A to B?
By moving a vector around, you haven't changed the vector. I would only change the vector if I scaled it, if I made it bigger or smaller, if I changed its orientation. And so visually, this is B, this is A. So if I add A to B, the resulting vector, going head to tails, I'll do it in let me see, I'll do this green color, would look like this. It would look like that. Right, A. So if I add A to B, the resulting vector going head to tails. I'll do it in this green color. Would look like this. It would look like that. Right? So here we took all this trouble and I had to draw these straight lines to visually add these two vectors. This green vector is A plus B. Let's see if this green vector is the same thing that we got here. Let's see if it's the same thing as this. So we got -1 times I, so -1 is like here. And then we have 6j. 6j, let me do another color 6j would look like this. 6j looks like that. You put them heads to tails, and it would get something like this. And that is the green vector. And actually, just so you know, I know it didn't line up perfectly, and that's because I'm not drawing neatly, but these 2 points should actually be here if I were to have drawn this better. But I know this was very confusing. I had all these colors, but the whole point of it is I wanted to show that, you could visually draw vectors and then have, shift them around and then put them heads to tails and then get the resulting vector. That's one way to add vectors, and there's still no way to analytically represent it. Or you could just write any vector as its x and y components, and then the sum of the vectors is just going to be the sum of the x's and then the sum of the y's. And that's a much cleaner and a much easier and much less prone to error way of adding or subtracting, really, 2 vectors. So hopefully that was convincing that a plus b really is this vector. If it wasn't, I'm sorry, and I hope I didn't confuse you more. But now that we have this out of the way, and hopefully you're convinced that unit vector notation is useful, we can move on and maybe try to do some of our old projectile motion problems using this notation, and maybe it'll let us to do a little bit extra stuff with it. See you soon.
The least amount of displacement. think it's I think it's D, but I'm not sure. I'm not entirely sure. Maybe I drew these wrong. Double magnitudes. C. Let's see if that's maybe what it is. Minus. How do you subtract? How do you do subtracting? What the heck? Oh. Actually, I think it's this. Oh, okay. That's what I was thinking, actually. Okay. And what about yeah, F is on line. Actually, F is also short, huh? And then N is D. D goes down, so we go up. Let's see. Down left and then plus E. Down left, right? Down left. A, B, A, B, E. I'm gonna get back to here. Is A on right plus D down plus E. Oh, but we started. I think it's because we started at A. Gotcha. And for D, it's A, D, and E. It's strange because if I do A here and then D, it's different. Oh, actually, the maybe. This is something flipped. A. Either way. I got yeah, that's actually pretty close to what I got. C plus C plus F minus D. Yeah, that's what I got. A plus D plus E. That's what I got there too. So let's see. D is too large, and C was also too large, right? A minus B plus E. I mean, J was too large. B was too large. A plus D plus E. C plus F. C plus F minus D. This one was too large. Uh-huh. Yeah, that's what I got. Sure. Alright, I can use this one. I don't know, these are my drives right here. A little kind of wacky. Whatever. It's kind of wacky. A little cool. I drink too much soda. back. Sorry. Use the restroom. Oh. Oh. Wrong one. I was looking at the wrong one. Never mind. Never mind. Oh no! Wait, it's right. Oh man. Oh man. Yeah, that's C. This is B right here. Minus day 6 14 that way. We're going to go the opposite way. Minus B. Oh wait, yeah, I think so. It's kind of strange, but yeah. Maybe C sounds pretty good. And then T is up. E plus D. Oh, wait. Maybe not actually. 3, 6. And T is. What was it? I think it's D. But if it's not, then it could be C. No T. Let's go. Let's go. Good stuff, man. Good stuff. Ow. Vector analysis. Vector analysis. Vector analysis. And forces acting on an object. Yes, sir. Woo. What the heck? Torque, magnetic force, power, torque, magnetic force, power. Maybe 2, 2 and 3. I trust 2. I not trust 2. Scalar and scalar. Oh, scalar and scalar. Product? Vector product? I don't know. Torque. I'm guessing torque, right? Maybe 2 and 2, 1 and 2. 1 and 2 are 1. Oh, 2 and 3. Oh. Gosh, what's capacitance? What's capacitance? Maybe capacitance? Charge or voltage? So then it's going to be torque. Um, let's go. Scalar multiplied by a vector can be scalar multiplied by a vector. Scalar multiplied by a vector. Excuse me. I don't remember if it was only for right angles or not. Maybe A or D. Oh, what? A must be flipped. A must be flipped. Okay. Yeah. What about it? Oh. some sort of force being acted upon it that's increasing the velocity, right? So the most likely being shot upstream because we lose. Make this difference. Change in velocity. I don't know how we know this, but something is being acted upon it. So I think it's changing. Well, this so we know ferry is traveling 94 meters per second. So, and this doesn't tell us if it's going against some sort of flow. Ow. Somebody more fluids of the sulfur. Maybe. Um. Maybe. All right. All right, let's take a 10-minute and then we'll keep going. See if we can do 4 lessons today. Yeah. I'll be back. I think we finished lesson 2. We'll work out a little bit. Oh, wrong one. Okay, cool. Hold on, guys. I gotta do this. Yeah, forgot. Hold on. I'll be right.
know a little bit about vectors.
A little bit about vectors and velocity and speed.
And scalars. Let's try to apply what we know about them for some pretty common problems you'd want to see in a physics class, but they're also common problems you'd see in everyday life because you're trying to figure out how far you've gone or how fast you're going or how long it might take you to get someplace. So first I have, if Chapuis was able to travel 5 kilometers north in 1 hour in his car, what was his average velocity? So one, let's just review a little bit about what we know about vectors and scalars. So they're giving us that he was able to travel 5 kilometers to the north. So they gave us a magnitude, that's the 5 kilometers, that's the size of how far he moved, and they also give a direction. So he moved a distance of 5 kilometers. Distance is the scalar, but if you give the direction to, you get the displacement. So this right here is a vector quantity. He was displaced 5 kilometers to the north. And he did it in 1 hour in his car. What was his average velocity? So velocity, there's many ways that you might see it defined, but velocity, once again, is a vector quantity. And the way that we differentiate between vector and scalar quantities is we put little arrows on top of vector quantities. Normally they're bolded if you can have a typeface, and they have an arrow on top of it. This tells you that not only do I care about the value of this thing, I care about the size of this thing, I also care about its direction. That's what the arrow. The arrow isn't necessarily its direction, it just tells you that it is a vector quantity. So the velocity of something is its change in position, including the direction of its change in position. So you could say its displacement, and the letter for displacement is S, and that is a vector quantity. So that is displacement. And you might be wondering, why don't they use D for displacement? That seems like a much more natural first letter. And my best sense of that is once you start doing calculus, you start using D for something very different. You use it for the derivative operator, and that's so that the D's don't get confused. And that's why we use S for displacement. If someone has a better explanation of that, feel free to comment on this video, and then I'll add another video explaining that better explanation. So velocity is your displacement over time. If I wanted to write an analogous thing for the scalar quantities, I could write that speed. And I'll write out the word so you don't get confused with displacement. Or maybe I'll write rate. Rate is another way that sometimes people write speed. So this is the vector version if you care about direction. If you don't care about direction, you would have your rate. So this is rate or speed is equal to the distance that you travel, over some time. So these two, you could call them formulas or you can call them definitions, although I would think that they're pretty intuitive for you. How fast something is going, you say, how far did it go over some period of time? These are essentially saying the same thing. This is when you care about direction, so you're dealing with vector quantities. This is where you're not so conscientious about direction, and so you use distance, which is scalar, and you use rate or speed, which is scalar. You use displacement, and you use velocity. Now, with that out of the way, let's figure out what his average velocity was. And this keyword average is interesting because it's possible that his velocity was changing over that whole time period. But for the sake of simplicity, we're going to assume that it was kind of a constant velocity, or what we are calculating is going to be his average velocity. But don't worry about it. You can just assume that it wasn't changing over that time period. So his velocity is, his displacement was 5 kilometers to the north. So his displacement, the displacement was 5 kilometers. I'll write just a big capital. Well, let me just write it out. 5 kilometers north over the amount of time it took him. Let me make it clear. This is change in time. Sometimes this is also change in time. Sometimes you'll just see a T written there. Sometimes you'll see someone actually put this little triangle, the character delta in front of it, which explicitly means change in. It looks like very fancy mathematics when you see that, but a triangle in front of something literally means change in. So this is change in time. So it goes 5 kilometers north And it took him 1 hour. So the change in time was 1 hour. Let me write that over here. So over 1 hour. So this is equal to, if you just look at the numerical part of it, it is 5 over 1. Let me just write out 5 over 1 kilometers, and you can treat the units the same way you would treat the quantities of a fraction. 5 over 1 kilometers per hour, and then to the north. Or you could say this is the same thing as 5 kilometers per hour north. So this is 5 kilometers per hour to the north. So that's his average velocity, 5 kilometers per hour. And you have to be careful. You have to say to the north if you want velocity. If someone just said 5 kilometers per hour, they're giving you a speed or a rate or a scalar quantity. You have to give the direction for it to be a vector quantity. You can do the same thing if someone just said, what was his average speed over that time? You could have said, well, his average speed or his rate would be the distance he travels. The distance, we don't care about the direction now. It's 5 kilometers, and he does it in 1 hour. His change in time is 1 hour. So this is the same thing as 5 kilometers per hour. So once again, we're only giving the magnitude here. This is a scalar quantity. If you want the vector, you have to do the north as well. Now you might be saying, hey, in the previous video, we talked about things in terms of meters per second. Here, I gave you kilometers or kilometers, depending on how you want to pronounce it. Kilometers per hour. What if someone wanted in meters per second? Or what if I just wanted to understand how many meters he travels in a second? And there it just becomes a unit conversion problem. And I figure it doesn't hurt to work on that right now. So if we wanted to do this to meters per second, how would we do it? Well, the first step is to think about how many meters we are traveling in an hour. So let's take 5 kilometers per hour, and we want to convert it to meters. So I put meters in the numerator and I put kilometers in the denominator. And the reason why I do that is because the kilometers are going to cancel out with the kilometers. And how many meters are there per kilometer? Well, there's 1,000 meters for every 1 kilometer. 1,000 meters for every 1 kilometer. And I set this up right here so that the kilometers cancel out. So these two characters cancel out, and if you multiply, you get 5, and then the only unit you have in the 5,000. So you have 5 times 1,000. So this is, so we write this 5 times, I'll do the same color, 5 times 1,000. So I just multiply the numbers. When you multiply something, you can switch around the order. Multiplication is commutative. I was probably pronouncing that associative. And then in the units, in the numerator, you have meters. And in the denominator, you have hours. Meters per hour. And so this is equal to 5,000 meters per hour. And you might say, hey, Sal, I know that 5 kilometers is the same thing as 5,000 meters. I could do that in my head, and you probably could. But this canceling out what's often called dimensional analysis right here can get useful once you start doing really, really complicated things with less intuitive units than something like this. But you should always do an intuitive gut check right here. You know that if you do 5 kilometers in an hour, that's a ton of meters, right? So you should get a larger number if you're talking about meters per hour. And now when we want to go to seconds, let's do an intuitive gut check. If something is traveling a certain amount in an hour, it should travel a much smaller amount in a second, or 1/3600th of an hour, because that's how many seconds there are in an hour. So that's your gut check. We should get a smaller number than this when we want to say meters per second. Let's actually do it with the dimensional analysis. So we want to cancel out the hours, and we want to be left with seconds in the denominator. So the best way to cancel this hours in the denominator is by having hours in the numerator. So you have hours per seconds. So how many hours are there per second? Or another way to think about it, 1 hour, think about the larger unit. 1 hour is how many seconds? Well, you have 60 seconds per minute times 60 minutes per second. The minutes cancel, times 60 minutes per hour, I should say. Times 60 minutes per hour. The minutes cancel out. 60 times 60 is 3,600 seconds per hour. 3,600 seconds per hour. Or if you flip it, so you could say this is 3,600 seconds for every 1 hour. Or if you flip them, you would get 1/3,600 hours, or hour per second, or hours per second, depending on how you want to do it. So 1 hour is the same thing as 3,600 seconds. And so now this hour cancels out with that hour, and then you multiply or appropriately divide the numbers right here, and you get this is equal to 5,000 over 3,600 meters per all you have left in the denominator here is second, meters per second. And if we divide, this is equal to 1.39 meters per second. 1.39 meters, 1.39 meters per second. So Shantanu was traveling quite slow in his car. Well, we knew that just by looking at this. 5 kilometers per hour, that's pretty much just like the car roll pretty slowly. Let's work through another few scenarios involving displacement, velocity, and time, or distance, rate, and time. So over here we have Ben is running at a constant velocity of 3 meters per second to the east. 3 meters per second to the east. And just as a review, this is a vector quantity. They're giving us the magnitude and the direction. If they just
I don't know what happened to my other pen. My big one, you know what I'm talking about? Because this one's going to run out.
just said 3 meters per second, then that would just be speed. So this is the magnitude. Magnitude is 3 meters per second, and it is to the east. So they are giving us the direction. So this is a vector quantity, and that's why it's velocity instead of speed. How long will it take him to travel 720? How long will it take him to travel 720 meters? So let's just remind ourselves a few things. And I'll do it both with the vector version of it, and maybe they should say, how long will it take him to travel 720 meters to the east? To the east, to make it clear that it is a vector quantity, so that's displacement as opposed to just distance. But we'll do it both ways. So one way to think about it, if we think about just the scalar version of it, we said already that rate or speed is equal to the distance that you travel over some time. I might write t there, but it's really a change in time. So sometimes some people would write a little triangle, a delta there, which means change in time. But that's implicitly meant when you just write over time like that. So rate or speed is equal to distance divided by time. Now, if you know, they're giving us in this problem, they're giving us the rate. If we think about the scalar part of it, they're giving us the rate. They're telling us that that is 3 meters per second. And they are also telling us the time. Oh, sorry, they're not telling us the time. They're telling us the distance, and they want us to figure out the time. So they tell us the distance is 720 meters. 720 meters. And so we just have to figure out the time. So if we just do the scalar version of it, we're not dealing with velocity and displacement. We're dealing with rate or speed and distance. So we have 3 meters per second is equal to 720 meters. 720 meters over some change in time. So we can algebraically manipulate this. We can multiply both sides times time. Multiply both sides times time. Multiply time right over there. And then we could, if we wanted, well, let's just take it one step at a time. So 3 meters per second. 3 meters per second times time is equal to 720 meters. Is equal to 720 meters, because the times on the right will cancel out right over there. And that makes sense, at least units-wise, because time is going to be in seconds. Seconds cancel out the seconds in the denominator, so you'll just get meters. So that just makes sense there. So if you want to solve for time, you can divide both sides by 3 meters per second. So divide both sides by 3 meters per second. 3 meters per second. And then the left side, they cancel out. On the right-hand side, this is going to be equal to 720 divided by 3 times meters. That's meters in the numerator. They had meters per second in the denominator. If you bring it out to the numerator, you take the inverse of this. So that's meters we do the meters that was on top, if we do that in green, we color code it. So 720 meters, and now you're dividing by meters per second. That's the same thing as multiplying by the inverse, times seconds per meters. And so what you're going to get here, the meters are going to cancel out, and you're going to get 720 divided by 3 seconds. So what is that? 720 divided by 3, 72 divided by 3 is 24. So this is going to be 240. This part right over here is going to be 240. It's going to be 240 seconds. That's the only unit we're left with. And on the left-hand side, we just had the time. So the time is 240 seconds. Sometimes you'll see it, and just to show you, in some physics classes, they'll show you all these formulas. But one thing I really want you to understand as we go through this journey together is that all of those formulas are really just algebraic manipulations of each other. So you really shouldn't memorize any of them. You should always say, hey, that's just manipulating one of those other formulas that I got before. One of those, and even these formulas are hopefully reasonably common sense. And so you can start from very common sense things. Rate is distance divided by time, and then just manipulate it to get other hopefully common sense things. So we could have done it here. So we could have multiplied both sides by time before we even put in the variables, and you would have gotten, so if you multiplied both sides by time here, you would have got on the right hand side, distance is equal to time times rate, or rate times time. And this is you'll often see this as kind of the formula for rate, or the formula for motions. If we flip it around, you get distance is equal to rate times time. So these are all saying the same things. And then if you wanted to solve for time, you could divide both sides by rate, and you get distance divided by rate is equal to time. And that's exactly what we got. Distance divided by rate was equal to time. So if your distance is 720 meters, your rate is 3 meters per second. 720 meters divided by 3 meters per second will also give you a time of 240 seconds. If we want to do the exact same thing with the vector version of it, just the notation will look a little bit different, and we want to keep track of the actual direction. So we could say, we know that velocity, and it is a vector quantity, so put a little arrow on top. Velocity is the same thing as displacement, let me pick a nice color for displacement, blue. As displacement, remember, we use S for displacement. We don't want to use D, because when you start doing calculus, especially vector calculus, well, any type of calculus, you use D for the derivative operator. If you don't know what that is, don't worry about it right now. But this right here, S is displacement. Displacement. At least this is convention. You can kind of use anything. This is what most people use. If you don't want to get confused, or if you don't want to be confused when they use S, it's good to practice with it. So it's displacement per time. So it's displacement divided by time. Sometimes, once again, you'll have displacement per change in time, which is really a little bit more correct. But I'll just go with the time right here, because this is the convention that you see, at least in most beginning physics books. So once again, if we want to solve for time, you can multiply both sides by time, and you get, this cancels out, you get, and I'll flip this around. Well, actually, I'll leave it like this. So you get displacement is equal to, I can flip these around, velocity times change in time, I should say, or we'll just say times to keep things simple. And if you want to solve for time, you divide both sides by velocity. And then that gives you time is equal to displacement divided by velocity. And so we can apply that to this right over here. Our displacement is 720 meters to the east. So in this case, our time is equal to 720 meters to the east. 720 meters east is our displacement, and we want to divide that by the given velocity. Well, they give us the velocity of 3 meters per second to the east. 3 meters per second to the east. And once again, 720 divided by 3 will give you 240. And then you have, when you take meters in the numerator and you divide by meters per second in the denominator, that's the same thing as multiplying by seconds per meter. Those cancel out, and you're just left with seconds here. One note I want to give you. In the last few problems, I've been making vector quantities by saying to the east or going north. And what you're going to see as we go into more complex problems, and this is what you might see in typical physics classes or typical books, is that you define a convention. That maybe you'll say the positive direction, especially when we're just dealing with one dimension, whether you can either go forward or backwards or left or right. We'll talk about other vector quantities when we can move in 2 or 3 dimensions. They might take some convention, like positive means you're moving to the east, and maybe negative means you're moving to the west. And so that way it'll make, well, in the future we'll see it'll make the math a little bit. The math will produce the results that we see a little bit better. So if this would just be a positive 720 meters, this would be positive 3 meters per second. And that implicitly tells us that that's the east. If it was negative, it would then be to the west. Something to think about. We're going to start exploring that a little bit more in future videos. And we might say positive is up, negative is down, or who knows. There's different ways to define it in one dimension. Let's do one more example dealing with displacement, velocity, and time. So we have, if Marcia travels for 1 minute at 5 meters per second to the south, how much will she be displaced? And so we know that velocity, this way, we know that velocity is equal to displacement divided by time. It's really, once again, it is change in time, but we'll just say time. That's implicitly change in time. And if you manipulate this a little bit, you really just multiply both sides by time. You just multiply both sides by the variable t. You get displacement, because this cancels out. You get displacement, and I'll flip this around. I'll write what's on the right hand. What's on the right hand side, I'll write on the left. So you get displacement is equal to time times velocity, or velocity times time, is equal to velocity times time, or velocity times change in time. So over here, they're asking us for displacement. They're asking us how much did Marcia get displaced. And they're saying that she travels for 1 minute. So this 1 minute right over here, this is her time. Sometimes you could do that as her change in time, or it really is her change in time. Whatever, if it said 0 minutes on her stopwatch when she started, at the end it'll say 1 minute. Or if it said 5 minutes, and maybe it was 3:05 when she started, it would be 3:06 when she finished. It was really the change in time. Once again, I won't write the delta there, just because it keeps it. This is the way you most frequently see it. But I want to tell you that these are the same thing for the purpose of this problem, because sometimes you'll see the delta there. So the 1 minute, so the t right over here is 1 minute. 1 minute at 5 meters per second to the south. At 5 meters per second to the south. This right over here is the velocity. They give us the magnitude, which is 5 meters per second, or you can say that's the speed. And they also give us the direction, to the south. So this right over here is 5 meters per second to the south. So we might just say, look, hey, if we want displacement, that's just going to be equal to 5 meters per second to the south times 1 minute. Times 1 minute. Times 1 minute. The problem here is that when we're talking about displacement, we're going to think about a magnitude of how much it's moved. So it'll be a distance of some kind and some direction. We have our direction here, but we don't want any other units there. And if we just multiply this over here, we have a minute over here, but we have seconds in the denominator. You can't just cancel out a minute and a second. So you can't just say you're going to get 5 and have some weird thing here. So in order for it to all work out, you have to either convert the 5 meters per second to 5 meters per minute, or let me create that another way. You have to convert the 5 meters per second to some amount of meters per minute, not 5 meters per minute, it's going to be different. Or you convert the 1 minute to seconds. So at least in my mind, it's easier to convert 1 minute to seconds. So let's do that. So this is the same thing, 1 minute times, and we want to get rid of the minute. And the minute is essentially the numerator right now. We can put this over 1. It's essentially the numerator. So we want to divide by minutes. We want to divide by minute, and we want to multiply by seconds. We want seconds in the numerator. And so what is How many seconds are there per minute? You have 60 seconds for every 1 minute. So you have the minutes canceling out the minutes. And so now you have 5 meters per second to the south times 60 seconds. This is now cool because you have seconds and seconds. I wrote SEC there, but this is also SEC. So now you have seconds over seconds. Those cancel out. And so your displacement is going to be equal to 5 times 60. 5 times 60. And then your units left are meters. All the time units have canceled out, and then it's meters to the south. So meters to the south, and this is equal to 5 times 60 is 300 meters to the south. And we are done. That's how much she has been displaced. If they just wanted the distance, you could say that she traveled 300 meters. Just that part. The magnitude of the displacement, that is the distance that she traveled.
Pretend you were a physics student. You were just getting.
In this video, this right here is a picture of an Airbus A380 aircraft.
You were just getting out of class. You were walking home when you remembered that there was a Galaxy Wars marathon on tonight. So you'd do what every physics student would do: run. You're pretty motivated to get home, so say you start running at 6 meters per second. Maybe it's been a while since the last time you ran, so you have to slow down a little bit to 2 meters per second. When you get a little closer to home, you say, "No, Captain Antares wouldn't give up, and I'm not giving up either," and you start running at 8 meters per second,
Whoa.
and you make it home just in time for the opening music. These numbers are values of the instantaneous speed. The instantaneous speed is the speed of an object at a particular moment in time. These numbers are values of the instantaneous speed. The instantaneous speed is the speed of an object. At a particular moment in time. And if you include the direction with that speed, you get the instantaneous velocity. In other words, 8 meters per second to the right was the, and if you include the direction with that speed, you get the instantaneous velocity. In other words, 8 meters per second to the right was the instantaneous velocity of this person at that particular moment in time. Note that this is different from the average velocity. If your home was 1,000 meters away from school and it took you a total of 200 seconds to get there, average velocity. If your home was 1,000 meters away from school and it took you a total of 200 seconds to get there, your average velocity would be 5 meters per second. Which doesn't necessarily equal the instantaneous velocities at particular points on your trip. In other words, let's say you jogged 60 meters in a time of 15 seconds. During this time, you were speeding up and slowing down and changing your speed at every moment. Regardless of the speeding up or slowing down that took place during this path, your average velocity is still just going to be 4 meters per second to the right, or if you like, positive 4 meters per second. Say you wanted to know the instantaneous velocity at a particular point in time during this trip. In that case, you'd want to find a smaller displacement over a shorter time interval that's centered at that point where you're trying to find the velocity at a particular point in time during this trip. In that case, you'd want to find a smaller displacement over a shorter time. Time interval that's centered at that point where you're trying to find the instantaneous velocity. This would give you a better value for the instantaneous velocity, but it still wouldn't be perfect. In order to better zero in on the instantaneous velocity, we could choose an even smaller displacement over that even shorter time interval. But we're going to run it into a problem here, because if you want to find a perfect value for the instantaneous velocity, you'd have to take an infinitesimally small displacement divided by an infinitesimally small time interval. But that's basically 0 divided by 0, and for a long time, no one could make any sense of this. In fact, since defining motion at a particular point in time seemed impossible, it made some ancient Greeks question whether motion had any meaning at all. They wondered whether motion was just an illusion. Eventually, Sir Isaac Newton developed a whole new way to do math that lets you figure out answers to these types of questions. Today, we call the math that Newton invented calculus. So if you were to ask a physicist, what's the formula for the instantaneous velocity? He or she would probably give you a formula that involves calculus. But in case some of you haven't taken calculus yet, I'm going to show you a few ways to find the instantaneous velocity that don't require the use of calculus. The first way is so simple that it's kind of obvious. If you're lucky enough to have a case where the velocity of an object doesn't change, then the formula for average velocity is just going to give you the same number as the instantaneous velocity at any point in time.
Yeah, that makes sense. Never changed. It never changed.
If your velocity is changing, one way you can find the instantaneous velocity is by looking at the motion on an x. Versus t graph. The slope at any particular point on this position versus time graph is going to equal the instantaneous velocity at that point in time, because the slope is going to give the instantaneous rate at which x is changing with slope is going to give the instantaneous rate at which x is changing with respect to time. Instantaneous rate at which x is changing with respect to time. A third way to find the instantaneous velocity is for another special case where the acceleration is constant. If the acceleration is constant, you can use the kinematic formula to find the instantaneous velocity v at any time t.
That's true. Turn it off. No music. Uh-oh. Uh-oh. Oh, I guess let me get some water. Yeah. These restrooms on side. Yeah. Be the ball, young grasshopper. You must be the ball. 스윙을 못하네. Slow. Stomach shake. See the finish for today. One. Two, three, four. 2, 3, 4, 2, 3. Oh, okay. Sure. I don't know, but for now we got some food. Oh. I also have to dry my eyes. I mean, water my eyes. My eyes are too dry. Yeah. Lock, drop, shot, and play.
In this video, I want to talk a little bit about acceleration. Acceleration. This is probably an idea that you're somewhat familiar with, or at least you've heard the term used here or there. Acceleration is just the change in velocity over time. Change in velocity. Velocity over time. Probably one of the most typical examples of acceleration, if you're at all interested in cars, is that many times they will give you acceleration numbers, especially for sports cars. Actually, all cars. If you look up in Consumer Reports or wherever they give the stats on different cars, they'll tell you something like, I don't know, like a Porsche. And I'm going to make up these numbers right over here. So let's say that we have a Porsche 911. Porsche 911. They'll say that a Porsche 911, they'll literally measure it with a stopwatch, can go 0 to 60 miles per hour. And these aren't the exact numbers, although I think it's probably pretty close. 0 to 60 miles per hour in, let's say, 3 seconds. In 3 seconds. So, although officially what they're giving you right here are speeds, because they're only giving you magnitude and no direction, you can assume that it's in the same direction. I mean, we could say 0 miles per hour to the east to 60 miles per hour to the east in 3 seconds. So what was the acceleration here? So I just told you the definition of acceleration. It's change in velocity over time. So the acceleration, and once again, acceleration is a vector quantity. You want to know not only how much is velocity changing over time, you also care about the direction. It also makes sense because velocity itself is a vector quantity. It needs magnitude and direction. So the acceleration here, and we're just going to assume that we're going to the right, 0 miles per hour and 60 miles per hour to the right. So what is it's going to be change in velocity. Let me just write it down in different notation just so you can familiarize yourself if you see it in the textbook this way. So change in velocity. This delta symbol right here just means change in velocity over time. Over time. It's really, as I've mentioned in previous videos, it's really time is really a change in time. We can just write time here. This 3 seconds is really a change in time. It might have been if you look at your second hand, it might have been 5 seconds when it started, and then it might have been 8 seconds when it stopped. So it took a total of 3 seconds. So time is really a change in seconds. But we'll just go with time right here. So which is the t. So what's our change in velocity? So our final velocity is 60 miles per hour. Our final velocity is 60 miles per hour. And our original velocity was 0 miles per hour. So it's 60 minus 0 miles per hour. And then what is our time? What is our time over here? Well, our time is, or we can even say our change in time. Our change in time is 3 seconds. 3 seconds. So this gives us 20 miles per hour per second. We write this down. So this top part is 60. 60 divided by 3 is 20. So we get 20, but then the units are a little bit strange. We have miles. Instead of writing mph, I'm going to write miles per hour. That's the same thing as mph. And then we also, in the denominator right over here, have seconds, which is a little bit strange. And as you'll see, the units for acceleration do seem a little bit strange, but if we think it through, it actually might make a little bit of sense. So miles per hour, and then we can either put seconds like this, or we could write per second. And let's just think about what this is saying, and then we could get it all into seconds, or we could all get into hours, whatever we like. This is saying that every second, this Porsche 911 can increase its velocity by 20 miles per hour. So its acceleration. is 20 miles per hour per second. And actually, we should include the direction. We're talking about vector quantities. So this is to the east. So this is east. And then this is east right over here. Just so we make sure that we're dealing with vectors. You're giving it a direction, due east. So every second, it can increase in velocity by 20 miles per hour. So hopefully the way I'm saying it, it makes a little bit of sense. 20 miles per hour per second. That's exactly what this is talking about. Now, we could also write it like this. This is the same thing as 20 miles per hour. Because if you take something and you divide it by seconds, that's the same thing as multiplying it by 1 over seconds. So that's miles per hour, seconds. And although this is correct, to me this makes a little less intuitive sense. This one literally says that every second it's increasing in velocity by 20 miles per hour. 20 miles per hour increase in velocity per second. So that kind of makes sense to me. Here it's saying 20 miles per hour seconds. So once again, it's not as intuitive. But we can make this so it's all in 1 unit of time, although you don't really have to. You can change this so that you get rid of maybe the hours in the denominator. And the best way to get rid of an hour in the denominator is by multiplying it by something that has hours in the numerator. So hour and seconds. And here, the smaller unit is the seconds. So it's 3,600 seconds for every 1 hour. Or 1 hour is equal to 3,600 seconds. Or 1/3600th of an hour per second. All of those are legitimate ways to interpret this thing in magenta right over here. And then you multiply and do dimensional analysis. Hour cancels with hour, and then you have this will be equal to 20 over 3,600. 20 over 3,600 miles per seconds times seconds. Or we could say miles, let me write this way, miles per seconds times seconds, or we can say miles per second. I'm going to do that in another form. Miles per second squared. Miles per second squared. And we can simplify this a little bit, divide the numerator and the denominator by 10. You get 2 over 360, or you could get this is the same thing as 1 over 180 miles per second squared. I'll just abbreviate it like that. Now, once again, this doesn't make 1/180th of a mile. How much is that? You might want to convert it to feet. But the whole point in here is I just wanted to show you that, well, one, how do you calculate acceleration, and give you a little bit of a sense what it means. And once again, this right here, when you have seconds squared in the bottom of your units, it doesn't make a ton of sense. We can rewrite it like this up here. This is 180, or 1 over 180 miles per second, and then we divide by seconds again, per second, or maybe I could write it like this, per second. This is where this whole thing is the numerator. So this makes a little bit more sense from an acceleration point of view. 1 over 180 miles per second. Every second, this Porsche 911 is going to go 1/180th of a mile per second faster. And actually, it's probably more intuitive to stick to the miles per hour, because that's something that we have a little bit of more sense on. And another way to visualize it. If you were to be driving that Porsche and you were to look at the speedometer for that Porsche, and if the acceleration was constant, it's actually not going to be completely constant. And if you looked at the speedometer, let me draw it. So this would be 10, 20, 30, 40, 50, 60. This is probably not what the speedometer for a Porsche looks like. This is probably more analogous to a small 4-cylinder car's speedometer. I suspect the Porsche's speedometer goes much beyond 60 miles per hour. But what you would see for something accelerating this fast is right when you're starting, the speedometer would be right there, and then every second it would be 20 miles per hour faster. So after a second, the speedometer would have moved this far. After another second, the speedometer would have moved this far. And then after another second, the speedometer would have moved that far. The entire time you would have kind of been pasted to the back of your seat. And I was curious, how long would it take this aircraft to take off? And I looked up its takeoff velocity. So takeoff velocity. And the specs I got were 280 kilometers per hour. And to make this a velocity, we have to specify a direction as well, not just a magnitude. So the direction is in the direction of the runway. So that would be the positive direction right over there. So when we're talking about acceleration or velocity in this, we're going to assume it's in this direction, the direction of going down the runway. And I also looked up its specs, and this I'm simplifying it a little bit because it's not going to have a purely constant acceleration. But let's just say from the moment that the pilot says we're taking off to when it actually takes off, it has a constant acceleration. Its engines are able to provide a constant acceleration of 1.0 meters per second. So after every second, it can go 1 meter per second faster than it was going at the beginning of that second. Or another way to write this is 1.0 meters per second or let me write it this way. Meters per second can also be written as meters per second squared. I find this a little bit more intuitive. This is a little bit neater to write. So let's figure this out. So the first thing that so we're trying to answer is how long does takeoff last? How long does takeoff last? That is the question we will try to answer. And to answer this, at least my brain wants to at least get the units right. So over here we have our acceleration in terms of meters and seconds, or seconds squared. And over here we have our takeoff velocity in terms of kilometers and hours. So let's just convert this takeoff velocity to meters per second, and then it might simplify this answering this question. So if we have 280 kilometers per hour, how do we convert that to meters per second? So let's convert it to kilometers per second first. So we want to get rid of this hours. The best way to do that, we have an hour in the denominator, we want an hour in the numerator, and we want a second in the denominator. And so what do we multiply this by, or what do we put in front of the hours and seconds? So 1 hour, in 1 hour there are 3,600 seconds, 60 seconds in a minute, 60 minutes in an hour. And so you have one of the larger unit is equal to 3,600 of the smaller unit. And so we can multiply by that, and if we do that, the hours will cancel out, and we'll get 280 divided by 3,600 kilometers per second. But I want to do all my math at once. So let's also do the conversion from kilometers to meters. So once again, we have kilometers in the numerator, so we want the kilometers in the denominator now, so it cancels out. And we want meters in the numerator. And what's the smaller unit? It's meters, and we have 1,000 meters for every 1 kilometer. So when you multiply this out, the kilometers are going to cancel out, and you're going to be left with 280 times 1, so we don't have to write it down, times 1,000, times 1,000, all of that over 3,600, and the units we have left are meters. We have meters per, and the only unit we have left here is second, meters per second. So let's get my trusty TI-85 out, and I should calculate this. So we have 280 times 1,000, which is obviously 280,000, but let me just divide that by 3,600, and it gives me 77.7 repeating indefinitely. And it looks like I had 2 significant digits in each of these original things. I had 1.0 over here. Not 100% clear how many significant digits I have over here. Was the spec rounded to the nearest 10 kilometers, or was it exactly 280 kilometers per hour? Just to be safe, I'll assume that it's rounded to the nearest 10 kilometers. So we only have 2 significant digits here. So we should only have 2 significant digits in our answer. So we're going to round this to 78 meters per second. So this is going to be 78 meters per second, which is pretty fast. For this thing to take off, every second that goes by, it has to travel 78 meters, roughly 3/4 the length of a football field in every second. But that's not what we're trying to answer. We're trying to say, how long will takeoff last? Well, we could just do this in our head if you think about it. The acceleration is 1 meter per second, which tells us after every second, it's going 1 meter per second faster. So if you start at a velocity of 0, and then after 1 second, it'll be going 1 meter per second. After 2 seconds, it'll be going 2 meters per second. After 3 seconds, it'll be going 3 meters per second. So how long will it take to get to 78 meters per second? Well, it'll take 78 seconds. It will take 78 seconds, or roughly 1 minute and 18 seconds. And just to verify this with our definition of our acceleration, so to speak, just remember acceleration, which is a vector quantity, and all the directions we're talking about now are in the direction of this direction of the runway. The acceleration is equal, or acceleration is equal to change in velocity over change in time. Over change in time. And we're trying to solve for how much time does it take, or the change in time. So let's do that. So let's multiply both sides by change in time. You get change in time times acceleration is equal to change in velocity. And to solve for change in time, divide both sides by the acceleration. So divide both sides by the acceleration, you get change in time. I could go down here, but I just want to use all this real estate I have for here. Change in time is equal to change in velocity divided by acceleration. And in this situation, what is our change in velocity? Well, we're starting off with a velocity, or we're assuming we're starting off with a velocity of 0 meters per second, and we're getting up to 78 meters per second. So our change in velocity is the 78 meters per second. So our change in velocity is 70. So this is equal in our situation, 78 meters per second is our change in velocity. Now take the final velocity, 78 meters per second, and subtract from that the initial velocity, which is 0 meters per second, and you just get this, divided by the acceleration, divided by 1 meter per second, or 1 meter per second squared. So the numbers part are pretty easy. You have 78 divided by 1, which is just 78. And then the units, you have meters per second. And then if you divide by meters per second squared, that's the same thing as multiplying by seconds squared per meter, right? Dividing by something is the same thing as multiplying by its reciprocal. You can do the same thing with units. And then we see the meters cancel out, and then seconds squared divided by seconds, you're just left with seconds. So once again, we get 78 seconds, a little over a minute for this thing to take off. In the last video, we figured out that given a takeoff velocity of 280 kilometers per hour, and if we have a positive value for any of these vectors, we assume it's in the forward direction for the runway. Given this takeoff velocity and a constant acceleration of 1 meter per second, or 1 meter per second squared, we figured out that it would take an Airbus A380 about 78 seconds to take off. What I want to figure out in this video is, given all of these numbers, how long of a runway does it need? Which is a very important question if you want to build a runway that can at least allow Airbus A380s to take off. You probably want it to be a little bit longer than that, just in case it takes a little bit longer than expected to take off. But what is the minimum length of the runway given these numbers? So we want to figure out the displacement, or how far does this plane travel as it's accelerating at 1 meter per second squared to 280 kilometers per hour, or 278, or where did I write it over here? 278, I converted it over right over here. As it accelerates to 78 meters, per second. How much land does this thing cover? So we can say, so let's call this the displacement, is going to be equal to, so displacement is equal to, you could view it as velocity times time, but the velocity here is changing. So we don't have if we just had a constant velocity for this entire time, we could just multiply that times however long it's traveling, and it would give us the displacement. But here our velocity is changing. But lucky for us, we learned, and I would encourage you to watch the video on y distance, or the video on average velocity for constant acceleration. But if you have constant acceleration, and that is what we are assuming, in this example. So if you assume that your acceleration is constant, then you can come up with something called an average velocity. And the average velocity, if your acceleration is constant, if and only if your acceleration is constant, then your average velocity will be the average of your final velocity and your initial velocity. And so in this situation, what is our average velocity? Well, our average velocity, let's do it in meters per second, is going to be our final velocity, which is, let me calculate it down here. So our average velocity in this example, velocity average in this example, is going to be our final velocity, which is 78 meters per second, plus our initial velocity. Well, what's our initial velocity? We're assuming we're starting at a standstill, plus 0, all of that over 2. So our average velocity in this situation, 78 divided by 2, is 39 meters per second. And the value of an average velocity, if we have, in this situation, actually average velocity in any situation, but in this situation we can calculate it this way. But the value of an average velocity is we can figure out our displacement by multiplying our average velocity, times the time that goes by, times the change in time. So we know the change in time is 78 seconds. We know our average velocity here is 39 meters per second. 39 meters per second. Just the average of 0 and 78, 39 meters per second. Another way to think about it, that if you want to think about the distance traveled, this plane is constantly accelerating. Let me draw a little graph here. This plane's velocity time graph would look something like this. So this is time, and this is velocity right over here. This plane has a constant acceleration starting with 0 velocity. It has a constant acceleration. This slope right here is its constant acceleration. It should actually be a slope of 1, given the numbers in this example. And the distance traveled is the distance that is the area under this curve up to 78 seconds. That's how long it takes for it to take off. So the distance traveled is this area right over here, which we'll cover in another video, or we give you the intuition of why that works and why distance is area under a velocity time line. What an average velocity is some velocity, and in this case it's exactly right in between our final and our initial velocities, that if you take that average velocity for the same amount of time, you would get the exact same area under the curve, or you would get the exact same distance. So our average velocity is 39 meters per second times 78 seconds. Let's just get our calculator out for this. Get our calculator out. We have 39 times 78. 78 gives us 3,042. So this gives us 3,042, and then meters per second times second just leaves us with meters. So you need a runway of 3,000, over 3,000 meters for one of these suckers to take off, or over 3 kilometers, which is like about 1.8 or 1.9 miles just for this guy to take off, which I think is pretty fascinating. to have something moving with a constant velocity of 5 meters per second. And we're just assuming it's moving to the right to give us direction, because this is a vector quantity, so it's moving in that direction right over there. And let me plot its velocity against time. So this is my velocity. So I'm actually going to only plot the magnitude of the velocity. You can specify that like this. So this is the magnitude of the velocity. And then on this axis, I'm going to plot time. So we have a constant velocity of 5 meters per second. So its magnitude is 5 meters per second. 5 meters per second. And it's constant. It's not changing. As the seconds tick away, the velocity does not change. So it's just moving 5 meters per second. Now, my question to you is, how far does this thing travel after 5 seconds? So after 5 seconds, so this is 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds right over here. So how far did this thing travel after 5 seconds? Well, we can think about it two ways. One, we know that velocity is equal to displacement over change in time. And displacement is just change in position over change. So this is change in position over change in time. Or another way to think about it, if you multiply both sides by change in time, you get velocity times change in time is equal to displacement. So what was the displacement over here? Well, I know what the velocity is. It's 5 meters per second. And it's 5 meters per second. That's the velocity of the color movements. That is the velocity. And we know what the change in time here. It is 5 seconds. It is 5 seconds. And so you get the seconds cancel out the seconds. You get 5 times 5, 25 meters. Is equal to 25 meters. And that's pretty straightforward. But the slightly more interesting thing is that's exactly the area under this rectangle right over here. That is exactly this area right over here. And what I'm going to show you in this video, that is in general, if you plot velocity, the magnitude of velocity, so you could say speed versus time, but let me just stay with the magnitude of the velocity versus time. The area under that curve is going to be the distance traveled, or the displacement, because displacement is just velocity times the change in time. So you just take out a rectangle right over there. So let me draw a slightly different one where the velocity is changing. So let me draw a situation where you have a constant acceleration. The acceleration over here is going to be 1 meter per second. So 1 meter per second squared. And let me draw the same type of graph. I'll just look a little different now. So this is my velocity axis. That's a little bit more space. And this is my velocity axis. So I'm just going to draw the magnitude of the velocity. And this right over here is my time axis. So this is time. Let me mark some stuff off here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the magnitude of velocity is going to be measured in meters per second. And the time is going to be measured in seconds. Time is going to be measured in seconds. So what's going to happen here, assuming that we start with, so my initial velocity, or I can say the magnitude of my initial velocity, so just this, my initial speed, you could say, this is just a fancy way of saying my initial speed is 0. So my initial speed is 0. So after 1 second, what's going to happen? After 1 second, I'm going 1 meter per second faster. So now I'm going 1 meter per second. After 2 seconds, what's happened? Well, now I'm going another meter per second faster than that. After another second, if I go forward in time, if change in time is 1 second, then I'm going a second faster than that. And if you remember the idea of slope from your Algebra 1 class, that's exactly what the acceleration is in this diagram right over here. The acceleration, we know that acceleration is equal to change in velocity over change in time. Over here, change in time is along the x-axis. So this right over here is a change in time, and this right over here is a change in velocity. So in this when we plot velocity or the magnitude of velocity relative to time, the slope idea of slope from your Algebra 1 class, that's exactly what the acceleration is in this diagram right over here. The acceleration, we know that acceleration is equal to change in velocity over change in time. Over here, change in time is along the x-axis. So this right over here is a change in time, and this right over here is a change in velocity. So this, when we plot velocity or the magnitude of velocity relative to time, the slope of that line is the acceleration. And since we're assuming the acceleration is constant, we have a constant slope. So we have just a line here. We don't have a curve. Now what I want to do is think about a situation. Let's say that we accelerated 1 meter per second squared, and we do it for so the time, so the change in time is going to be 5 seconds. And my question to you is, how far have we traveled? Which is a slightly more interesting question than what we've been asking so far. So we start off with an initial velocity of 0, and then for 5 seconds we accelerated 1 meter per second squared. So 1 is where we go. This is where we are. So after 5 seconds, we know our velocity. Our velocity is now 5 meters per second. 5 meters per second. But how far have we traveled? So we can think about it a little bit visually. We could say, look, we could try to draw rectangles over here. We were at maybe right over here, we had a velocity of 1 meter per second. So if I say 1 meter per second times a second, that'll give me a little bit of distance. And then the next one, I have a little bit more of distance. Calculate it the same way. And I can keep drawing these rectangles here. But then you're like, wait, those rectangles are missing there, because I wasn't, for the whole second, I wasn't only going 1 meter per second. I kept accelerating. So actually, I should maybe split up the rectangles. I could split up the rectangles even more. So maybe I go every half second. So on this half second, I was going at this velocity, and I go at that velocity for a half second. Velocity times the time will give me the displacement. And then I do it for the next half second. Same exact idea here. Give me the displacement. So on and so forth. Well, I think what you see as you're getting is the more accurate, the smaller the rectangles you try to make here, the closer you're going to get to the area under this curve. The area under this curve. And just like the situation here, this area under the curve is going to be the distance. Traveled. The distance traveled. And lucky for us, this is just going to be a triangle, and we know how to figure out the area for a triangle. So the area of a triangle is, area of a triangle is equal to 1/2 times base times height, which hopefully makes sense to you, because if you just multiply base times height, you get the area for the entire rectangle, and the triangle is exactly half of that. So the distance traveled in this situation, the distance traveled, or I should say the displacement, just because we want to make sure we're focused on vectors, the displacement here is going to be, or I should say the magnitude of the displacement maybe, which is the same thing as the distance, is going to be 1/2 times the base, which is 5 seconds, times the height, which is 5 meters per second, times 5 meters. Let me use that in that other color. 5 meters per second. 5 meters per second. The seconds cancel out with the seconds, and we're left with 1/2 times 5 meters. So it's 1/2 times 25, which is equal to 12.5 meters. And so there's an interesting thing here. Well, one, there's a couple of interesting things. Hopefully you realize that if you're plotting velocity versus time, the area under the curve, given a certain amount of time, tells you how far you have traveled. The other interesting thing is that the slope of the curve tells you your acceleration. What's the slope over here? Well, where it's completely flat. And that's because the velocity isn't changing. So in this situation, we have a constant acceleration. The magnitude of that acceleration is exactly 0. Our velocity is not changing. Here we have an acceleration of 1 meter per second squared, and that's why the slope of this line right over here is 1. The other interesting thing is even if you have constant acceleration, you can still figure out the distance by just taking the area under the curve like this. We were able to figure out that we were able to get 12.5 meters. The last thing I want to introduce you to, actually, let me just do it until the next video, and I'll introduce you to the idea of average velocity. Now that we feel comfortable with the idea that the distance you traveled is the area under the velocity versus time curve. The goal of this video is to explore some of the concepts or formulas you might see in a traditional physics class, but even more importantly, to see that they're really just common sense ideas. So let's just start with a simple example. Let's say that, and for the sake of this video, just so I don't have to keep saying this is the magnitude of the velocity, this is the direction of the velocity, et cetera, let's just assume that if I have a positive number, that it means, for example, if I have a positive velocity, it means that I am going to the right. And let's say if I have a negative number, which we won't see in this video, let's assume that I'm going to the left. And that way I can just write a number down. We're only operating in one dimension. You know that it's specifying both the magnitude and the direction. If I say that the velocity is 5 meters per second, that means 5 meters per second to the right. If I say it's negative 5 meters per second, that means it's 5 meters per second. The goal of this video is,
hold on. Wake up, Shaquille O'Neal. Wait, buddy, thank you. Wait, buddy, thank you so much. I'll be back, hold on.
to explore some of the concepts or formulas you might see in a traditional physics class, but even more importantly, to see that they're really just common sense ideas. So let's just start with a simple example. Let's say that, and for the sake of this video, just so I don't have to keep saying this is the magnitude of the velocity, this is the direction of the velocity, et cetera, let's just assume that if I have a positive number, that it means, for example, if I have a positive velocity, it means that I am going to the right. And let's say if I have a negative number, which we won't see in this video, let's assume that I'm going to the left. And that way I can just write a number down. We're only operating in one dimension. You know that it's specifying both the magnitude and the direction. If I say that the velocity is 5 meters per second, that means 5 meters per second to the right. If I say it's negative 5 meters per second, that means it's 5 meters per second to the left. Now let's just say, just for simplicity, let's just say that we start with an initial velocity. We start with an initial velocity of 5 meters per second. And once again, I am specifying both the magnitude and the direction because of this convention here. We know it is to the right. And let's say that we have a constant acceleration. We have a constant acceleration at play of 2 meters per second, or 2 meters per second squared. And once again, since this is positive, it is to the right. And let's say that we do this for a duration, so per second. And once again, I am specifying both the magnitude and the direction because of this convention here. We know it is to the right. And let's say that we have a constant acceleration. We have a constant acceleration at play of 2 meters per second, or 2 meters per second squared. And once again, since this is positive, it is to the right. And let's say that we do this for a duration. So my change in time is, let's say we do this for a duration of 4, I'll use the same 4, I'll just use S. So I don't use seconds and then sec and then S in different places. So S for this video is seconds. So what I want to do is think about how far do we travel? And well, there's two things. How fast are we going after 4 seconds, and how far have we traveled over the course of those 4 seconds? So let's draw ourselves a little bit of a diagram here. So this is my velocity axis, and this over here is my time axis. I can draw up a straighter line than that. So that is my time axis. Time, this is velocity. It's clipping off the left hand. That is my velocity right over there. And I'm starting off at 5 meters per second. So this is 5 meters per second right over here. So VI is equal to 5 meters per second. And then every second that goes by, I'm going 2 meters per second faster, because this is 2 meters per second. So every second that goes by, so after 1 second, I'm going to go 2 meters per second faster. So I'll be at 7. Or another way to think about it is the slope of this velocity line is my constant acceleration, or I have a constant slope here. So it might look something like that. So what has happened after 4 seconds? So 1, 2, 3, 4. So this is my delta t. So my final velocity is going to be right over there. So my final velocity is going to be right over there. I'll write it down here just because it's getting in the way of this word velocity. And so this is v. This is my final velocity. And what would it be? Well, I'm starting at 5 meters per second. So I'm going to do it both using the variables and using the concrete numbers. So I'm starting at some initial velocity. The subscript I says I for initial. And then each second that goes by, I'm getting this much faster. So if I want to see how much faster have I gone, I multiply the number of seconds. I'll just multiply the number of seconds that go by times my acceleration. Times my acceleration. And once again, this right here, I just wrote the subscript C saying that it's a constant acceleration. And so that will tell me how fast I've gone. If I start at this point and I multiply the duration times my slope, I will get this high. I will get to my final velocity. And just to make it clear with the numbers, these numbers really could be anything. I'm just picking these to make it concrete in your mind. You have 5 meters per second plus 4 seconds plus, I'm going to do that in yellow, plus 4 seconds times our acceleration of 2 meters per second squared. 2 meters per second squared. And what is this going to be equal to? You have a seconds canceling out with one of the seconds down here. You have 4 times, so let me write it. So we have 5 meters per second plus 4 times 2 is 8. 8, this second's gone. We're just left with meters per second. 8 meters per second. Or this is the same thing as 13 meters per second, which is going to be our final velocity. And I want to take a pause here, and you can pause and think about it yourself. This hopefully should be intuitive. We were starting at going 5 meters per second. Every second that goes by, we're going to go 2 meters per second faster. So after 1 second, we'll be at 7 meters per second. After 2 seconds, we will be at 9 meters per second. After 3 seconds, we will be at 11 meters per second. And then after 4 seconds, we will be at 13 meters per second. So you multiply how much time passed times acceleration. This is how much faster we're going to be going. We're already going 5 meters per second. 5 plus how much faster? 13 meters per second. So this right up here is 13 meters per second. So I'll take a little pause here. Hopefully that's intuitive. And the whole point of that is to show you that this formula that you'll often see in many physics books, it's not just something that randomly popped out of the air. It just makes complete common sense. Now, the next thing I want to talk about is what is the total distance that we would have traveled? And we know from the last video that distance is just the area under this curve right over here. So it's just the area, under this curve. You say, wait, this is kind of a strange shape right here. How do I calculate its area? And we can just use a little simple geometry to break it down into 2 different areas that are very easy to calculate their areas, or 2 simple shapes. You can break it down into this blue part, this rectangle right over here. Easy to figure out the area of a rectangle. And we could break it down into this purple part, this triangle right here. Easy to figure out the area of a triangle. And that will be the total distance we travel. And even this will hopefully make some intuition, because this blue area is how far would we have traveled if we were not accelerating, if we just went 5 meters per second for 4 seconds. So if you go 5 meters per second times, so this is 1 second, 2 second, 3 second, 4 second. So you're going from time 0 to time 4. Your change in time is 4 seconds. So if you go 5 meters per second for 4 seconds, you're going to go 20 meters. This right here is 20 meters. That is the area of this right here, 5 times 4. This I guess purple or magenta area tells you how further than this are you going because you're accelerating, because you kept going faster and faster and faster. It's pretty easy to calculate this area. The base here is still 5, because that's 5 seconds have gone by. And what's the height here? The height here is my final velocity minus my initial velocity. Or it's the change in velocity due to the acceleration. And the change in velocity due to the acceleration, 13 minus 5 is 8. Or it's this 8 right over here. It is 8. It is 8 meters per second. So this height right over here is 8 meters per second. The base right over here is 4 seconds. That's the time that passed. So what's the area of this triangle? The area of a triangle is 1/2 times the base, which is 4 seconds. 4 seconds times the height, which is 8 meters per second, times 8 meters per second. Seconds cancel out. 1/2 times 4 is 2, times 8 is equal to 16 meters. So the total distance we traveled is 20 plus 16 is 36 meters. That is the total, or I could say the total displacement. And once again, it's to the right since it is positive. So this is our displacement. Now, what I want to do is do this exact same calculation, but keep it in variable form, and that'll give another formula that many people often memorize. But I want you to understand that it's a completely intuitive formula, and it just comes out of the kind of the logical flow of reasoning that we went through this video. What is the area? Once again, if we use it if we just think about the variables, well, the area of this rectangle right here is our initial velocity times our change in time times our change in time. So that's the blue. This is the blue rectangle right over here. And then plus, what do we have to do? We have the change in time. Once again, we have the change in time times this height, which is our final velocity, which is times our final velocity minus our initial velocity, These are all vectors. Oh, they're just positive, telling us we're going to the right. And if we just don't multiply the base times the height, that would give us the area of this entire rectangle. We have to take it by half because the triangle is only half of that rectangle. So times 1/2. So times 1/2. And so this is the area. This is the purple area. It's not purple. This is the purple area right over here. This is the area of this. This is the area of that. And let's simplify this a little bit. Let's factor out a delta t. So if you factor out a delta t, you get delta t times a bunch of stuff, v sub I. So your initial velocity, we factored this out, plus this stuff, plus this thing right over here. And we can distribute the 1/2. We factored the 1/2. We factored the delta t's out. That's why we're taking it out. And let's multiply the 1/2 times each of these things. So it's going to be plus 1/2 times vf times our final velocity. That's not the right color. We should actually do it in the right color so that you understand what I'm doing. This is the 1/2. So plus 1/2 times our final velocity minus 1/2 times our initial velocity, minus 1/2 times our initial. I want to do that in blue. Sorry, I'm having trouble changing colors today. Minus 1/2 times our initial velocity, And now what does this simplify to? We have something plus 1/2 times something else minus 1/2 times that original something. So what is VI minus 1/2 times VI? So anything minus half of it is you're just going to have a positive half left. So these two terms, this term and this term, will simplify to 1/2 VI, 1/2 the initial velocity, plus 1/2 times the final velocity, plus 1/2 times the final velocity, and all of that is being multiplied by our change in time, or the time that has gone by. And this tells us the distance that we traveled. Or another way to think about it, let's factor out this 1/2. You get distance is equal to change in time times factoring out the 1/2 VI plus VF. VI, no, that's not the right color. VI plus VF. So this is interesting. The distance we traveled is equal to 1/2 of the initial velocity plus the final velocity. So this is really, if you just took this quantity right over here is just the arithmetic, I always have trouble saying that word. It's the arithmetic mean of these two numbers. And so I'm going to define this as something new. I'm going to call this the average velocity. We have to be very careful with this. This right here is the average velocity. But the only reason why I can just take the starting velocity and the ending velocity and adding them together and then divide by 2, essentially taking the average of these two things, which would be someplace over here, and I take that as the average velocity, is because my acceleration is constant, which is usually an assumption in most introductory physics classes, but it's not always the assumption. But if you do have a constant acceleration like this, you can assume that the average velocity is going to be the average of the initial velocity and the final velocity. If this was a curve, if the acceleration was changing, you could not do that. But what's useful about this is if you want to figure out the distance that was traveled, you just need to know the initial velocity and the final velocity, average the two, and then multiply that times the time that goes by. So in this situation, our final velocity is 13 meters per second. Our initial velocity was 5 meters per second. So you have 13 plus 5 is equal to 18. You divide that by 2. Your average velocity is 9 meters per second if you take the average of 13 and 5. And then 9 meters per second times 4 seconds gives you 36 meters. So hopefully that doesn't confuse you. I just want to show you where some of these things that you'll see in your physics class, some of these formulas, why you shouldn't memorize them, and they can all be deduced.
Okay, guys, I think I'm gonna call here for today. Yeah, we can do more tomorrow. Kind of, yeah, yeah. We'll do more tomorrow. Do better tomorrow. It is what it is. All right, thanks so much for watching, guys. See you guys tomorrow.